Okay, so next thing that we are going to consider in this chapter are the race conditions. Now, when we talk about the asynchronous sequential circuits, we can say that race conditions exist when two or more binary state variables change their value in response to change in an input variable. So this is actually can be from unequal delays encountered. A race condition may cause the state variables to change in an unpredictable manner. So for example, if the state variables must change from 0, 0 to 1, 1, now as I mentioned before as well, so if we change them to 0, 0 to 1, 1 at the same time, the difference in delay may cause the first variable to change sooner than the second variable. So it might be a nanosecond difference over there, but it's actually going to affect the operation. So with the result that the state variables change in sequence from 0, 0, then 1, 0, and then 1, 1 will be better. Now, if the second variable changes sooner than the first, the state variables will change from then 0, 0 to 0, 1, and then 1, 1. So actually, when these are going from this state to that state, we don't actually know if this is occurring or that one is occurring. We don't know which one is changing first. So there are two types of race conditions. The one of them is non-critical race. So if the final state uh, uh, that the circuit reaches does not depend on the order in which the state variables change, so that's a non-critical one. Okay, so the final stable state does not depend on the sequence of state variable changes. But if it's a critical one, then the final stable state depends on the sequence of state variable changes. So we will see an examples related to these. And we start with the non-critical race. Now, when we look at the non-critical races, so we start with the total stable states. So where y1, y2 is 0, 0, and input is 0. Okay, so that's our stable state. Now, what we can see from here, we can see a possible transition. So state variable must change from 0, 0 to 1, 1, which actually going to define the race condition. Now, here we identify the stable state, so 0, 0, and 1, 1. Let's do this one first. Okay, so when present is 0, next is 0, when input is 0. And when present is 1, 1, and input is 1, next state is 1, 1. So we can identify those stable states. So what will be the possible transitions? Now, when we are in present state 0, 0, if we change the input from 0 to 1, we end up in 1, 1. So what will happen? We will jump down over here. Okay. Now, when we are in 1, 1, if the input is 1, we are ending up in 1, 1. That's first case. Now, when we are in 0, 1, if the input is changing from 0 to 1, again, from 1, 1, we will jump down to 1, 1 state. And when the input is 1, we can see that we are ending up in 1, 1. Or 1, 0. When the input is 1, again, this will end up in state 1, 1. So in all these conditions that the state variable may change, the final total state is 1, 1. And when the input is 1, so we can say 1, 1, 1. So this is the final total state. So 0, 0 to 1, 1, or 0, 0 to 0, 1, and then 1, 1, or 0, 0 to 1, 0, and then 1, 1, they all end up in 1, 1. If we look at this one, so the first possible transition from stable state 0, 0, when the input changes to 1, we jump to 1, 1. Now, when we are in 1, 1, if the input changes to 1, we jump to 0, 1. I go over here. And 0, 1, If the input is 1, we stay at 0, 1. Okay, so from stable state 0, 0, we can go to 0, 1. When the input is 1, we end up in 0, 1. 1, 0, when the input is 1, we go to 1, 1. And when the input is 1 again, we end up in 0, 1. So in all conditions, as you can see, again, we end up in 0, 1, where input is 1, so 0, 1, 1. So these are the final, this is the final total state, which is 0, 1, 1. Now, these are non-critical races, as you can see. We end up in the same states. And we also have critical races. With the critical races, as I already said, it's possible to end up in 2 or more different states, stable states, depending on the order which the state variable changes. So for proper operation, we should avoid these critical races. So let's see an example for critical races. Now, actually, this header has to be critical, not non-critical. Okay, now here, 0, 0, when the input changes, it ends up in 1, 1. 0, 1, input changes, ends up in 0, 1. 1, 1, input changes, end up in 1, 1. 1, 0, input changes, ended up in 1, 0. Okay, so as you can see, only when it is 0, 0 goes to 1, 1, and 1, 1 goes to 1, 1. The other ones are just ending up in different states. So if because of unequal propagation delay, there might be a case where the Y2 changes to 1 before Y1 does. Then the circuit goes to total stable state at 0, 1, 1 and remains. If, however, Y1 changes first, the internal state becomes 1, 0, and the critical circuit will remain in the internal state 1, 0, 1. Okay, so you can see the differences over here. You can identify those because our intention on these 2 points was ending up in 1, 1. But as one of those are changing earlier than the other one, they are ending up in a different places. This is critical race. And the same applies for the second example, where we have got 2 possible transitions result in 1 final state, but the third possible transition, which is this one, goes to a different total state. These are ending up in 1, 1, but this one ends up in 1, 0. Again, it is because of having one of the variables changing earlier than the other one. Because intention was 1, 1, but we end up in 1, 0. So these are some of the critical points. And races may be avoided. And how do we avoid these races? It's important. We can actually make a proper binary assignment to the state variables. We have to be careful that we are changing 1 bit at a time. And the state variables must be assigned to binary numbers in a way that only one state variable can change at any one time with a state transition occurs in the flow table. So as I already mentioned, fundamental modes of operation and so on, this is what we need to do. And races can be avoided by directing the circuit through intermediate unstable states with a unique state variable change. This is also possible to be avoiding critical races. Okay, so these were the critical races, and let's carry on. Unstable circuits. So what is unstable circuit? Now, when you look at this simple combinational circuit with a feedback path, let's write the next state equation for it, which is going to be x1 NAND y and x2. So that's our next state equation. Now, this next state equation, the question comes in as what happens when x1 and x2 are equals to 1? Right, so if we draw the K-map, where we have got 0, 0, 0, 1, 1, 1, 1, 0, and 0, 1. Now let's place those in. So we can rewrite this x1 prime or y1, y prime, okay, and that's going to be x2, which is going to be x1 prime x2 or y prime x2. So now when we place these in, where x1 is 0 and x2 is 1. x1 is 0 and x2 is 1 on those 2 points. And y is 0 and x2 is 1. Y is 0 and x2 is 1 at that point. And the rest are just zeros. Now, if we want to identify the stable states, when present is 0, next is 0, this is stable. Present is 0, next is 0, this is stable. Present is 1, next is 1, this is stable, and that's it. Now, when we look at each of these columns, column 0, 0 has got stable state, 0, 1 has got stable state, 1, 0 has got stable state. However, 1, 1 hasn't got any stable state because when present is 0, next is 1. When present is 1, next is 0. So this is actually no stable state in this case. So that means y is not equal to small y. The internal state keeps toggling until inputs change again to one of those from to 1, 0 or maybe to, so either to 0, 1 or to 1, 0. And this behavior is called cycle. Okay, and it can be used in oscillator circuits in order to generate a cycle. So it's like a toggling all the time. It's possible. So this is how unstable circuits can be done. Okay, so next thing that we are going to consider are designed using SR latches. If you do remember SR latches in chapter 5, they are actually latch, they are not clocked, so it looks like they are asynchronous sequential circuits. They are actually. And we know the states when both inputs are 0, there's no change. When reset is 1, output will be resetted to 0. When set is 1, output is set to 1. And when both are 1, it's undefined. And the equation that we have derived previously from the K-map is you can do that with the OR gate, NOR gates as in a way that, so it will end up, if you write this equation, this is going to be SR prime or YR prime, okay? So we just write the circuit equation if you want. Or you can also derive the equation from the K-map, that's also possible. So in the NOR implementation, as you can see over here, the traditional method of asynchronous circuit configuration has been with the components that are connected to form one or more feedback loops. And when digital circuits are constructed with electronic components, it is convenient to employ a SR latch as a memory element. So that's why we are using SR latches in these cases. Now, when we look at these in the NOR implementation, where S and R is 1, the result is going to be an undefined because Q and Q primes are 0, so it violates. So going from SR 1, 1 to 0, 0 and vice versa is problematic. It's also timing sensitive. So to get a different stable state, depending on if the transition is 1, 1 to 1, 0 or 1, 1 to 0, 1, that will be different. So we can derive the transition table, as you can see over here. And this transition table is actually based on this equation here. So where S is 1, R is 0, okay? R is 0, S is 1, it's 1, and Y is 1, and R is 0 at those 2 points. And the stable states are those. Now, from the transition table, we observe that going from SNR 1, 1 to 0, 0, it produces an unpredictable result. Okay, so for example, if S goes to 0 first, okay, so if S goes to 0 first, then the output remains at 0. But if R goes 0 first, then the output goes to 1. So you can see that how they are ending up in an unpredictable manner. Okay? Now, in normal operation, we must make sure that ones are not applied to both S and NAR input simultaneously because of these undefined states. So this condition is actually can be expressed by the Boolean function where SNR equals 0 and ending SNR must always will equal to 0. Now, if we go back to the excitation function, and maybe I can show it from here. So if we go to the excitation function where y is equals s plus y r prime, we observe that when we order the Boolean expression sr prime with sr, the result is a single variable. So if we do this, sr prime or sr, this is going to end up in s r prime r, which is equals s, single variable. Now, as we are observing this, okay, we can say that when SR is equals S, when SR is equals 0. Okay, so this is a one observation that we can get it. Now, at this point, we can rewrite the excitation function as y is equals S R prime or y R prime as y is equals S or R prime y. So SR is reduced to S because of this. Okay? So again, when SR is equals 0 and ending SR must always be 0 in this case, then we can rewrite the expression, we can get this S from it. So when SR is 0, we can use this, and we must check if SR is 0, and we can use the reduced formula. If it's not, we just use the original formula. That's one thing that we need to make sure that it's SR or something, SR equals 0 or not. And the non-implementation is also similar. And in this case, we have to check where S and R is 1, results in Q and Q prime equals 1, which violates QQ prime. So SR11 to 0, 0, and vice versa is still problematic. And output is undefined for S and R, which is equals 1, or S prime, R prime, which is equals 0 input setting. Okay, so how are we going to derive the latch-based circuits? It's our next objective in this chapter. And derive a transition table for a problem at hand. Derive pair of K-maps or pair of maps, not K-maps, pair of maps so that S and R for each 1, 2, or K when we have got the next states Y1, Y2, and K using SR excitation table. We have to simplify it and we have to draw the logic diagram using SR functions. And one thing to understand this better is solving an example. So Y is equals x1, x2 prime, or x1, y. So we have got two inputs and one output. Let's start with the transition table. Okay, so here we have got x1, x2, 0, 0, 0, 1, 1, 1, 1, 0, and y, 0, 1. So y, x1, x2, and that's the capital Y. And let's place down the x1, x2 prime, so 0, 1, 0. 1, 0 is going to be 1, and x1 is 1, y is 1. x1 is 1, y is 1 at these 2 points. So that's going to be 1, and the rest are all just zeros. So this is our transition table. Let's identify the stable states. So the stable states, when it is 0, next is 0, next is 0. When it is 1, next is 1, and next is 1. Those are our stable state. So if you do remember the excitation table of SR, or maybe we can rederive it, present and to the next. So y, small y, capital Y, SR. So 0, 0, 0, 1, 1, 0, 1, 1. Right, so when present is 0, next is 0, means it's a, okay, let's do it this way. SR, Q, and Q next. Let's do this first, so that it will be easier to derive it. 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. This is the characteristic table for SR from chapter 5. Right. When both inputs are 0, then it's hold. When it is reset, so the output is 0, 0. When it is set, output is 1, 1. And the last one is unstable, which is X. Okay. And going back to our property, when present is 0, next is 0, that means either we are holding or we are resetting. So S is 0, as you can see, R is changing. So S is 0, R is changing, we just put don't care. Then when it is 0, 1, so present is 0, next is 1, that means it's a set. So in set, we know that S is 1, R is 0. Always. And 1 to 0 is reset, so we know that S should be 0 and R to be 1. And 1, 1, present is 1, next is 1. Either we are holding, let's change the color of this. Either we are holding or we are setting it. So S is changing, R is always 0. So X, 0. So that's our excitation table for SR. Now, as we know the excitation table for SR, now from the transition table, we can separate this transition table and find out what will be the S and R values are going to be. So I'll try to fit everything here if I can. Now I need to create a separate table for S and separate K-map, not table, for R actually. Zero 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 one 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 zero 0, and 0 1 0 1, then y x1 x2, y, x1, x2. So this is for S and this is for R. Now, so based on the flow table over here, I need to find one interesting color so that we can easily track. Okay, so present is 0, next is 0. 0, 0 means 0x. So S is 0, R is x. Present is 0, next is 0, 0x. 0, 0, 0x. And then 0, 1. 0, 1 is 1, 0. So S is 1, R is 0. I hope you can all follow that. Then 1, 0, it's 0, 1. So 0, 1. 1, 0, again 0, 1. 1, 1 is x 0. And 1, 1 is also x 0. So we have got all the points, and all we need to do is circle the ones that is required and write an expression. So S is x1, x2 prime, and R is just x1 prime. That's it. Now we have got the equations, and all we need to do is implement the circuitry using SR latch. So S is x1, x2 prime, R is x1 prime. Okay, so in this one, yeah, it's x1 prime. Then AND gate. So let's say this is x2, and x2 needs to be inverted. Hang on, let's take it a little bit further. x2 inverted, x1 feeding in, and that goes into S input, and R input is just x1 prime, and that will go into the R, and we have got Q and Q bar. So that will be the logic circuit using SR latch. That's how we can do an implementation using SR latches. I hope it is clear. Now, if you have any questions, please note those down and feel free to ask them during the live session. Right, so one last thing, or the one last section that we are going to cover in this chapter. So these are just showing the same steps and the implementation of it. And the analysis of asynchronous sequential network. So as you can see, the sequential network is given. We have to find out the transition equations and the output equations. And from those, we have to just make an analysis of by writing the flow table and the transition table, so we can check how each of these states are transitioning from one to another. Okay, so let's start with the transition equations. Now, y1 is x1, x2 prime, or x2, y1, y2 prime. x2, y1, y2 prime, or x1, x2, y2. x1, x2, y2. So that's our first equation. Then y2, it's going to be x1 prime, x2, y1 prime, x1 prime, x2, y1 prime, or x1, y2 prime, or x1, y2, sorry, or x2, y2. So these are the transition equations, and the output equation Z is just Y1 XOR Y2 XOR X1. So it's just XORing all those together. Now we have got all the equations required. Now we just need to have the transition table, flow table, and the output table. I'll try to fit everything here so that we can see all these together. So transition table, flow table, output table. As we have got 4 variables, we need 16 squares for all of these. So 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Okay, so, hang on. This has to be, as it is a flow table, it's just A, B, C, and D, because we are going to use letters. Okay, so I'll say transition, flow, output. Right, so let's start with the first one. Now we have got, maybe it's difficult to fit over here, but I'll show you from here that this is Y1, Y2, this is X1, X2. And here we just have S, X1, X2, X1, X2, and Y1, Y2. Okay then. So let's start with Y1, dark blue. So X1, X2 prime, X1, X1, X2 prime, so 1, 0. So 1, 0 will have ones for Y1. Let's write down Y1 first and then Y2 next to it. Then X2, Y1, Y2 prime. Y1, Y2 prime is here, and X2, where X2 is 1, are those 2 points. So that means these two are going to be ones. Then X1, X2, Y2. So X1 and X2 is 1, and Y2 is 1. So those 2 points, and these are going to be ones. And the rest are just zeros again. Okay, so Y2 is X1 prime, X2, Y1 prime. So 0, 1, which is this one, and Y1 prime is those two. So this is going to be, these are going to be ones. Then X1, Y2. X1 is 1 at these points, and Y2 is 1 at those points. So these are going to be ones. Then X2, Y2. So X2 is 1. X2 is 1 at these points, and Y2 is 1 on those points. So that's going to be 1 as well. So that's all we have got, and the rest are just zeros fed in. 0, 0, 0, 0, and 0 over there. So we have got the transition table. Let's fill out the state table. So 0, 0 is A, 0, 1 is B, 0, 0 is A, 1, 0 is D, 0, 1 0, 0, A, so these are all A's. 0, 1 is B and D, C, C, and D, and C, C, and D on those cases as well. And let's do the output. So output is just XORing of Y1 XOR Y2 XOR X1. So we are looking for the odds there. So when X1 is 1, and at this point, this is going to be 1, and this is going to be 1. So Y2 is 1, and at this point, X1 is 0, Y1 is 0, so that's going to be 1. And at this point, it's going to be 1, and those are going to be zeros. Then y1, y2, and x, so this is going to be 0, this is going to be 0, then triple ones, it's 1 and 1 over there. So y1 is 1, at this point those are going to be 1, and these are going to be zeros. So we have got output as well, the transition and the flow table. Now, identifying the states, stable states. So 0, 0, 0, 0, 0, 1, 1, 1, and 1, 0, 1, 0, 1, 0. And the same over here, A's, the B's, the C's, and D's. These are all stable states. So we have got the analysis part of it. Now, let's see from the slides as well how this is done. We have got all these points for now. And it says assume the initial state is 0, 0 and input is transitioning. So x1 and x2 is transitioning from 0, 0 to 0, 1, 1, 1 to 1, 0. Okay, let's do that. Let's change the color again. So when the input is 0, 0, we start from the initial state as 0, 0 from here. Okay, so from A, when the input is 0, 0, okay, so we jump from 0, 0 to 0, 1. So when it is 0, 1, we actually jump over here, we are jumping from A to B, okay? So when the input changes to 0, 1, then the next state is 0, 1. So that means it's gonna be, next state is going to be B. Now we jump down to B, 0, 1, and when it is 0, 1, so we jump down to B over here. When we are in B, when the input changes to 1, 1, we go to C. Okay, so from here we go to C, and when we are in C, that means we have to go down here. When we are in C, if the input is 1, 0, it stays at C. So this is going to be C as well. So you can see how the transition is happening, and we can also write down the output as well, because output is jumping this in a similar manner. So to 0, and then 1, and then 0, and then 1, and then 1 again. Okay, so this is going to be starting from, I don't know if I can fit over there, probably not. So starting from 0, and then it goes to 1, and then from 1, it goes to 0. Sorry, it jumps down to 1 again, and then from there it's also 1 again. But in between transitions are like 0, 0, and that is directly so 0 over there, 0 over there, and that's 1. Okay, and ending up in 1. So that's how we can actually find out the state transitions one by one when we are changing the input from 0, 0 to 0, 1 to B. Then when we are in B to 1, 1, that is C. So we jump down to C, and C 1, 0 will stay at C. And this is how we can get the analysis of the state transitions and the outputs. And also the timing waveform is given over here, where we can see how each state is changing and how this is affecting the x1, x2, and z, and that's our output as well. So 0, 0, when inputs are 0, 0, then the output is 0, 0, 0 output is 0, 0, 1, the output is 1, okay, and then 0, 1 output is 1, then 1, 1, it's going to be 0, and 1, 1, it's going to be 1 again. So one thing over here, like we have seen it before, there's a false output because we were expecting that to be 1 as well, because as this is going to be 0, 1, that has to be 1, okay? So we are having that problem here as well because of the false output, which is called glitch. So this is how we can analyze these circuits and derive the expressions and the flow and the transition tables and the output tables. That's all you need to know about this chapter. And for this term, that's all you need to have. Good luck in your exams. And if you have any questions, feel free to ask. Do not hesitate to contact me. Thank you.